All right, hey, I'm Nico. Welcome to this talk. I'm happy that I can give a presentation at the CCC Congress again. This presentation has actually been a joint work with my colleague and friend Kevin Redon, and yeah, so let's have a look at what I'm going to talk about today. So I will start this presentation giving you an overview about the GSM architecture, and given the history of GSM talks at this Congress, I promise to keep this as short as possible so you're not bored at the beginning. I will introduce what actually mobile paging is, which is like the main topic of this talk. And I will show various attacks against the paging procedures in GSM, ranging from attacking single subscribers as well as attacking large areas before I draw some conclusions. So she already mentioned that I explain why it still makes sense to look at GSM. GSM is, has been beaten to death. There's lots of problems with configuration issues deployed in real networks. The ciphers have all been broken except for A53. Dieter Spar has shown that it's possible to exhaust channels in BTSs. You can do various kinds of signaling attacks against these networks. So GSM is pretty much already dead, but still I think it's very interesting to see like how deep the rabbit hole goes. So it's still around, it will be around for the next 10 to 15 days, especially given all the M2M movement. And it's very unlikely that it dies. And one thing that makes it, for me, very interesting to look at GSM is that this protocol really forms the basis for a lot of newer protocols these days. So depending on what you actually look at, it may be that these issues still affect 3G and LTE, which I think may be true even for the stuff I'm showing here. And last but not least, there has been lots of movement in terms of GSM software and hardware. There's all kinds of projects that allow you to play with this stuff. So for me personally, it's just fun to play with radio. All right, let's look at the GSM architecture and the components that are like important for this. So I start on the left, which is the device you all know. So this is a mobile phone, which is talking to the base station over the air. So the base station is just the radio tower that transfers signal from your phone to the network and vice versa. And it's connected to the so-called base station controller, which is pretty much just a managing entity which manages several BTSs at once. And it talks to the mobile switching center, which is really the component in the network that takes care about everything which is related to establishing calls, switching a call from one location to the other, initiating signaling to the phone. And it's also usually connected to what's called the PSTN, which stands for Public Switch Telephony Network. So this is like the normal landline phone. And it's talking to two important components here. Actually, the VLR, which is the Visitor Location Register, is directly connected to an MSC usually. But before I explain that, I want to explain what the HLR is. So the HLR is the Home Location Register, and this is really like what the value is of a mobile operator. So this is where all the subscriber information is stored, every information which is relevant to billing. And this is where the information of your SIM card is stored and your phone number, and this is like a central subscriber database of an operator. The VLR is kind of serves the same purpose. So whenever you need subscriber information for a subscriber in some area, you don't want to contact like the central entity of the network, so you don't want to query the HLR always. So the VLR is pretty much like a local subscriber cache. So this talk is all about paging, so I think it makes sense to introduce what paging actually is. So in GSM, paging is mostly a procedure which allows the network to notify a subscriber that there's an incoming service. And by service, I mean just a phone call or text message. So in GSM terms, there is a paging channel, which is a broadcast channel, which is transmitted on the downlink, which is monitored by all phones. And this is used to transfer a message to phones which listen to this broadcast channel to let the phone know, hey, here's a service, please accept this service. And so on this paging channel, the network sends messages which are called paging requests. And those messages contain a mobile identity. And mobile identity basically has the interesting types for this talk are is that a temporary mobile subscriber identity and the international mobile subscriber identity. The International Mobile Subscriber Identity, IMSI, is basically just the identification of your SIM card. And because this information is transmitted over the air in clear text, operators don't use it that much because this obviously allows people who observe the air traffic to track subscribers and to determine whether you're in a specific area or not. So these days they use these TIMSIs, which are shorter numbers, which are temporary and which change, fairly frequently. And so this bypasses, this prevents tracking. So when a mobile phone is monitoring this paging channel and it sees such a message, what it does is it basically grabs the mobile identity from the paging request and compares it to its own identity. And if it matches, it has to react and establish a channel and basically start all the procedures which allow the phone to accept the service. So, as I said, this is a broadcast channel on the downlink, so it's interesting, can we actually abuse the knowledge of what subscriber is paged? In GSM networks, there is no thing such as an end-to-end connection from one phone to another. The network is basically differing between mobile originating services, which is when your phone is sending a message to the network, and it's switching the message and transfers the message to the phone. And the transfer between the network and to the destination phone is called mobile terminated service. So this is when the network tries to deliver a phone call or an SMS, and this is what this talk is about. So it's all about mobile terminated services. The important part here is that a mobile phone is not in constant contact with the network. So while the network kind of has a clue where you are, it doesn't know which base station is currently providing the best reception level to the phone. So the reason they do this is mostly to save battery. And the only situation where the phone actually lets the network know where it currently is exactly is when it changes a larger location, which is called location area. So this is like really a geographical area. So the network has to determine which BTS is actually providing the best reception level to the phone, and all of this is stored in the visitor location register. So the VLR is the entity which organizes these location areas and knows that the phone is in location area X. So let's have a look at what actually happens when someone is trying to call a subscriber and how this call is delivered. So first you have a phone, you do a phone call of the phone, which is on the left, and you have to find out which VLR and which MSC is actually handling the subscriber. So that the HLR doesn't know exactly which location area the phone is in, but it knows which MSC and VLR is responsible for this area. So you query for this information, or the core network is querying this information when it wants to transmit a phone call to the phone. Afterwards, it just contacts the mobile switching center or the VLR to find out what really the exact location is, which are the base stations which are responsible for this area. And for this, the MSC will contact the VLR and determine the location area which is currently serving the subscriber. This is like the last known location of the subscriber. And this returns a number of base stations and cell identifiers which are responsible for this area. So the next step is the mobile switching center will initiate a paging command to the base station controller, which says, hey, please transmit paging in exactly this area for the BTSs which serve this area. The BSC will then go and transmit it to all base stations that are serving this area, and the base stations take this message. The message already contains the mobile identity of the subscriber, and the base stations wrap it up in what's called the paging request, which is the message which is transmitted over the air. So the BTSs will transmit this message, but it's important that this is not transmitted to only the phone, but like from all base stations within that area. So this is not seen by one phone. This is why we have multiple phones on the left side, and they are all camping on their cells and monitoring this paging channel. So each base station is providing one paging channel. So they see the paging request which arrives over the air, and they have to check if the mobile identity contained in the paging request is their own. So dead beef is like a TIMSY example here. So they compare this value, and if it matches, the one phone which owns this identity is initiating a channel request on the random access channel. This is a shared uplink channel. It needs to do that because the network doesn't start automatically transferring the service, but the phone needs to establish a signaling channel in order to do the call setup with the network. If the network has the required resources to actually transmit the service, it will answer the paging request with an immediate assignment on the access grant channel, which is a shared downlink channel. And in order that the phone is able to actually know that the immediate assignment message on this channel is for itself, this message contains a random reference which also was sent in the channel request message. So it can compare this because every phone is again seeing this immediate assignment. So it knows, okay, now the network is providing a channel for me and I can tune to this frequency and accept the service. So this is what's happening then. In the next step, the network is tuning to this dedicated signaling channel to establish the call setup and sends a paging response message back to the network. So that this is just the signal to the network which says, okay, I'm here, I can accept the service, please deliver the service to me. Afterwards, so at this point, and this is actually important to keep in mind for a later step in the presentation, the phone doesn't ring yet because the phone doesn't know if this is an SMS message or a call. So before it knows that, the network wants to authenticate the subscriber because it doesn't want to deliver a service to any phone in the area. Which isn't true in practice because it's not always authenticated, but more on that later. When this is happening, most networks these days encrypt all the messaging, and then there's a step of ciphering, and afterwards the service is actually delivered. The phone knows now it can ring because it's a call, or just accepts the SMS message. So the interesting part here is obviously what stops the subscriber to just respond to paging requests which are directed to other phones. Can't we just use this to hijack, for example, a service? And in reality, this is not so easy because the authentication and ciphering step that I mentioned is based on a secret which is stored on the SIM card. So what actually happens in practice is the network is sending a random challenge to the phone, which is combined with the secret key on the SIM card and is producing a response which is sent to the network so the network can verify whether the subscriber is really authenticated. And this also forms the basis for the encryption which comes later. So if we want to hijack a service for another subscriber, we can't just do that because we don't have the SIM card, so we can't compute the response, and we also can't do the ciphering with the network. But the interesting part here is what actually happens once you send bad data back to the network. So obviously the network can't establish the service, it can't deliver it to you, so it will drop the channel and no service is delivered. So this is bad. But actually the nice thing about this is that this is a race condition, right? So if you respond to a paging request for another subscriber, the network, or it's an implementation defined on how the network reacts to that. So in practice, there's a lot of complex state machines in the GSM protocols, and phones as well as networks implement those. So states change all the time, and especially states change once you drop a service and once you drop a channel. And also if you receive a paging response. So the interesting question here is what happens actually if the network receives two paging responses, and if we reply faster than the actual phone who should receive the service, how does the network react, and will it still expect the second paging response by the actual victim phone? And it's also interesting to note here that unlike other attacks against base stations or denial of service attacks in GSM, this is not limited to one BTS. You don't have to be in the same cell as the victim because the paging is broadcasted in this location area thingy, which I will explain a bit more later. So if we can respond faster, we may have a denial of service problem here. And the question is, what exactly is fast? So speed for radio transmission is influenced by various things. So you have obviously weather. So if it's raining, the signal is not transmitted as good as if it's not raining. But those are all factors that are not too important in terms of speed. So this is not like a difference of 0.1 seconds or something. But what actually makes the difference in practice is what's called the baseband implementation. Excuse me. The baseband is, in modern smartphones, usually a dedicated chip which runs its own operating system and protocol stack, which takes care about all the radio signaling. And it's usually comprised of 3 layers. Layer 1 is just the radio transmission over the air. Then you have layer 2, which is a link layer, and layer 3, which implements all the protocol logic like paging requests and paging responses and accepting calls and all of this. And between those layers, like whenever you have a layered system, there's queuing and scheduling involved, and depending on how you implement this is what I thought, and I think it's true, makes a difference in terms of speed. So how would you actually implement a very fast baseband, or how would you implement your own baseband firmware at all? And this is where all the recent movement from the GSM open source community comes into play, because there is actually a free software open source baseband, which is called Osmocom BB, which you can modify so you have your own baseband implementation. It also runs on real hardware, which you see there. So this is an example of the Motorola C123. There's also other Motorola phones that can run this baseband. And they are really cheap. You can buy them for 5 to 20 euros. And there's also an application which is called mobile application, which already implements basically a phone. So you could modify that to respond to paging for other subscribers and see how it reacts. In practice, as you will see, this is way too slow because the mobile application in Osmocom is running on a PC and communicating with the layer 1 firmware on the phone over a serial line, and this is not really the fastest. So what we did here to actually implement the very fast baseband is we took the layer 2 and the layer 3 of the mobile application, or basically everything which is required to handle paging and establish a service, and re-implemented that in the layer 1 firmware. So it runs completely on the device itself. So it's very fast, and we will see how fast it is in a bit. So what this attack phone is doing, it just camps on a cell, it monitors the paging channel, and it reacts to paging requests. So it can react to a paging request for a specific TIMSI, to a specific IMSI, or to a range of those numbers. And afterwards, it performs invalid ciphering or authentication, so it actually causes the network to drop the channel so that the call or the text message is not delivered. So before we actually say that this is feasible in practice and we can respond faster, we somehow need to determine what is like the speed of the average phone in practice. So, like I said, the speed is mostly made up by the baseband implementation. And looking at the market of smartphones, there's a couple of interesting basebands to look at. So the list you see here is actually all the baseband. There's more basebands in general, but those are the baseband manufacturers which actually have a baseband deployed in phones that you can buy on the market. So we wanted to take a phone for each of those and measure the speed. The way we did this is we took the USRP, which is the hardware you see there, which is basically just a radio transceiver, which is completely controlled by software. The software which actually can run this is called OpenBTS, which implements a small subset of the GSM network stack. And we're interested in 2 types of timing information here to find out if we actually are faster. So we're interested in the time between the paging request popping up on the air interface and the victim phone establishing a channel to the network, and we are interested in the overall time when the paging response by the victim phone arrives at the network. So the way we do this is we just hook up phones to the BTS, we send SMS messages to them because the SMS message will create a paging request over the air, and we just measure the speed. So this is what this looks like. On the left side, on the y-axis, you have the time in milliseconds, which is required to either respond with a channel request or with a paging response. So those are all phones that we tested, and I think there's a couple of interesting things to note here, which also kind of prove that my theory about the baseband actually making what the speed shows. So the Nokia 3310 on the left side, for example, is almost 10 years older than the Nokia N900 on the right side here. But as you see, they are pretty much the same in terms of speed. And the way I explain this is that GSM stacks are really old, and baseband manufacturers these days concentrate on implementing 3G and LTE, so there's not much modifications going on anymore. So the age of the speed the age of the phone doesn't influence the speed too much. The new phone doesn't mean it's very fast. For example, as you see here for the Sony Xperia U, this is really a new phone and it's not fast either. The other thing which you see here is the Osmocom BB Layer 2.3 version of the phone, which is the mobile application, is kind of around the speed of a real phone. So it's not really fast and you have no chance to win this race condition by using the mobile application of Osmocom BB, or at least not against like the average phone. And most important in this graph is our Layer 1 firmware, which is supposed to be really fast, is also really fast. As you see here, it responds way faster with the channel request and with the paging response to the network than all the other phones. And also interesting here is that the timing difference between the channel request and the paging response is really small. And I again think that this is because there's no scheduling and queuing involved. If we receive a message from the network, we just respond right away and we don't need to put this in a queue and some other layer of the software needs to pick up the message and send it. So we have a pretty good chance to win this race in practice, and I try to test this with all the major operators in Germany. So this is Vodafone, O2, E+, and T-Mobile, and all of them are vulnerable to this attack, which is, I think, pretty bad. So what this means is you have a denial of service attack against mobile terminated services. So basically, when responding faster to a paging request, you can prevent that the service is delivered to the victim. So you can basically just block a call or a text message. So this is like selectively jamming the transmission of the service. So I will show you how this looks like in practice. Yeah, I made a video here because I think if I just hold two phones here, it's pretty hard to see what's actually happening. So first, the victim is on the right-hand side here. So I first call the victim. Oh, actually, this is supposed to have subtitles. Anyway, so I call the phone on the right side, and what you see here is the paging messages on the air interface. So those are all TIMSIs, and while the code says the TIMSI doesn't match, here it found a match for the victim. But the attacking phone on the left side is not reacting at all. So first we see that there's subtitles. The call is working, the phone rings, so everything is fine. Now to attack the phone on the right side, we need to know to which paging request we have to react. So we need to know the TIMSI in this case. And this is why I use this old phone, because it has a nice net, net monitoring display where you can see the identity of the phone. Actually, it's not really visible. But what I will do with it, I will enter this into this script here, so the attacking phone knows to which TIMSI it reacts. So now you see here that the attacking phone noticed that the TIMSI changes and it wants to react to the paging. In order to do that, I changed the attack mode of the phone to do the paging attack. And try to call again. Yeah, this is in the E+ network, which apparently isn't the fastest. So you see already the ciphering message. Oh, okay, it was too fast, but you saw the ciphering messages, and in this mode, the phone doesn't react to the ciphering at all. What you can also do is you can react with wrong information. Yeah, the phone is not reachable. Okay, it tries a third time. It's still not reachable. So if you do this all the time, this is a permanent denial of service attack. And yeah, so the call is dropped again. And once I stop the attack again, the phone should be reachable again. And it is. Yeah. Okay, so this is why I say this is basically like selectively jamming. All right, so at this point you may say this is actually pretty lame because you have to know the identity of the phone, and how do I find this out? And in theory, you don't need to know this. I mean, what stops you from actually reacting to every paging request on the air interface? And I will explain more on that later. Then there's some networks which don't use the TIMSI at all, but use the IMSI instead, even because they don't care about tracking and privacy. And in this case, it's actually very easy because there is external services which allow you to do an HLR lookup. So you put in a phone number and it gives you the IMSI, and you can just use that and react to exactly those IMSIs. And even for TIMSIs, they are supposed to provide privacy, but it has been shown that this is actually not real in practice. So this is not, I didn't find this out, so this was published as part of a paper, and also Carsten Nohl and Sylvain Monod showed this in their wideband GSM sniffing talk. So what you can do basically to find out the TIMSI for a phone number is you use one of these Osmocom BB phones and you just camp it on a cell, and you monitor the paging channel in the area where you think the target phone may be in. And then you just use a second phone, you call the victim, and because what I said earlier, that in the initial stage of the paging protocol, the phone doesn't ring yet because it doesn't know what service is coming in, you just drop the call again, but early enough so that a paging is created and you can just see that. And once you repeat that, you have, of course, repeating patterns in terms of the TIMSI over the air as well, and then you can just correlate that with your call pattern and see what TIMSI that is. So getting the identity in practice really is no problem. Then I also mentioned that it would be really nice to hijack a service. So when I send an SMS message to, or when someone sends an SMS message to the victim, it would be really nice to not sniff it over the air, but really hijack it so that I have it, but the victim never received the message. And in practice, I said you need the session key KC for that, which is used for the encryption. And also you would need to respond to authentication, but more on that on the next slide. So how does encryption actually look like in networks these days? So in some countries, I was told that this may be true for some operators. And in India, you have no encryption at all. So this is A50. Then you have some networks are still using A52. So this is the GSM ciphering algorithm that got broken first because it's actually extremely weak. And then most networks these days use what's called A51. So this is currently deployed in all the German networks, and even this is insecure in practice. So people have broken it in theory before, and then people at the Congress at the 26C3 and 27C3 showed that it's really practical to crack the session key in almost in real time in a couple of seconds. And the output was also a tool called Kraken, which you can use. You can basically stuff in traffic which you sniffed from the air, either with a modified Osmocom BB phone or actually a set of Osmocom BB phones or air probe, and it just cracks the session key and outputs in a couple of seconds. So this is also no problem in practice. And while there is a solution which is called A53, which basically is a variant of A51 with a longer key length, this is not deployed in current networks at all. It will likely change in the future, but from what I know, it's not done so far because some phone manufacturers actually don't implement this correctly, so they couldn't use the network anymore if they enforce this encryption algorithm. So encryption in reality doesn't really prevent hijacking the service at all. So how about authentication? So referring to another talk by Carsten, which I'm not sure if actually Carsten gave the talk, but so his company, Security Research Labs, gave this presentation at the SIGINT conference this year. And they have this nice GSM map project which tries to monitor various aspects of GSM networks. And referring to them, in 50% of the networks they monitor, only in 10% of the cases mobile terminated services are authenticated. So this basically means that for 50% of their networks in 90% of the cases you can hijack the service, which is bad. And I think the reason for this is that mobile operators really only care about mobile originating, because this is what creates the billing. So when I send an SMS to someone, this creates money for them, and when I make a phone call, this also creates money for them, but they don't earn money by delivering a service, and this is pretty bad, even though I think that mobile terminated services also kind of affect the billing, because if you think about this at a global scale, if everyone can do a phone call but nobody can receive a phone call, no value is created either, with the exception that SMS is built on the submission of the message already. So incomplete authentication, and authentication is incomplete in most networks I've seen. I actually haven't seen much authentication for mobile terminated services at all. It is possible to hijack the service. Once you broke the encryption in our code, which we are also going to publish, you can feed a session key into the phone, and it's using it for the ciphering. So how does hijacking a service look like? So again, in this demo, we send an SMS message from the phone in the middle to the victim phone on the right. And just to show that this actually works, I send a test message before. So it received the message. It shows something that should be tested. And in the next step, now assume that I send some information that an attacker shouldn't get in the first place. So this is a message called secret. And I enable the attack on the attacking phone. So now I send the message, and now the phone on the right shouldn't receive the message because the attacking phone is hijacking the service. So let's watch the screen. So this is the secret. So the SMS is hijacked. Yeah. So I disable the attack again, just to show that the phone is still able to receive a message. Yeah, and the message arrived again. And just to point this out, I didn't sniff the message from the air interface and decrypted the traffic, but I really grabbed the SMS message so that the victim never received it. So I said that doing authentication all the time would solve this problem, and it would if, in practice, it would be implemented correctly. So for the German operator O2, they actually have a problem with authentication, because what happens is, or what I noticed during trying to winning this race is, when you send your paging response message to the network, and the network will respond with an authentication request that you can't answer because you don't have the SIM card, and you just don't do anything, you just wait. But because the victim at some point will also respond with a paging response message, and the network may also ask the phone to do an authentication. And once this happens and the victim replies to the authentication, you as an attacker are actually authenticated as well, which is pretty bad. I don't know why this is. The only reason I could see here is that the network only keeps state of an authenticated subscriber. So once you respond to the authentication, the subscriber is marked as authenticated, and the network continues to push the next messages through the channel, which in this case would be the ciphering, but that is no issue in practice. So all of this so far has been attacking either like a set of subscribers or single subscribers, but can't we just attack all the subscribers within one of these location areas? I mentioned you don't need the TIMSI, you can just respond to all paging requests. So we don't need to camp on the same BTS as the victims we want to attack. We just sit on one BTS and we respond to all paging requests for the whole location area. Of course, the effect is that nobody in this location area would be able to receive the service anymore. So to determine the impact of this, it would be actually nice to know like how large is one of these location areas. So just that you have an idea of what this means in practice. And the location area, or the identification for a location area, is actually part of a message which is transferred on a broadcast channel as well. So this is called the location area code. And by basically just using two people, a GPS logger and an application from Osmocom BB, which logs this broadcast information, a car, which is a picture of my car in this case, you can basically just map the entire location area by correlating the location area codes you've seen with the GPS data that you have. And this is what this looks like for Berlin. So yeah, Berlin is a major city, and this is an example for Vodafone. And as you can see here, there aren't too many location areas, and they're actually pretty large. So we have like 5 location areas here. And it's actually extremely nice that you can just sit here and attack a subscriber, which is somehow down here. So how large are these location areas? It actually depends on how the operator is planning the network. It depends on if you're in a city or if you're in a suburb somehow. So in non-city areas, we've seen location areas which are up to 1,000 square meters, which is really a huge area. But even in Berlin, the location areas are still between 100 and 500 square kilometers. So the impact really is huge. And the way network operators sometimes do the planning is that these location areas cover districts of a city. So if you could render mobile terminated services not working anymore in a city district, the impact would be pretty bad. And of course, one nice thing about this is that you can't just, I actually talked to a guy from an operator and he said, yeah, you can just buy a jammer and have a similar effect, but this is not true. You can't just use a jammer and jam such a large area over such a, or at least I haven't seen such a jammer, and especially not over this frequency range, because not all the BTSs are using the same frequency. And you would likely also affect wireless and all kinds of Wi-Fi and all kinds of other stuff. So this is not feasible. But the feasibility in practice depends on how much paging actually is in such a location area. So we measured this as well. So the way we do this is we used another Osmocom BB phone, and we just camp on a base station in the inner part of Berlin, basically. And we did this for each operator, so we camped on one BTS for all of them. We did this at the same location over 24 hours at the same time, and the result is what you see here. So on the y-axis here, you don't actually see the number of paging requests, because paging requests can contain more than one mobile identity, but you see the number of TIMSIs contained in those paging requests. And as you see here already, the amount of paging changes throughout the day, and what you basically see is human activity. So people stand up at 8 in the morning, they start to use their phone calls, you have a peak sometime in the afternoon, and the later the day gets, the less paging exists. So obviously, depending on the size and the amount of customers of the operator, the paging activity is different. So O2 and E+ are pretty small operators. The paging amount is way smaller than for T-Mobile and Vodafone. Vodafone actually has way more paging than T-Mobile, but this is because they are doing something really strange, because for whatever reason they are paging again exactly 2 seconds after the first paging. And the only explanation I have for this is that they just try to deliver more services in cases of any errors. So in theory, you could reduce the Vodafone line by half, and you will end up at a similar amount than for T-Mobile. The other thing that you may want to do if you attack a complete location area is you want to reduce the amount of paging over time, because otherwise you really have to take care about this huge amount all the time. And there's actually another attack which Sylvain Menot introduced at DeepSec, I think, which is called the IMSI detach attack. So an IMSI detach is the notification from your phone to the network that you're not reachable anymore. So if I switch off my phone, it sends this message to the network, and the network will not page this phone anymore until you reattach and tell the network, here I am again. And the nice thing about this signal is that it's not authenticated at all. So I can just yeah, so just by using the mobile identities contained in the paging request, you can first do the paging attack and then send an IMSI detach at some point afterwards, and you don't have to care about the subscriber again. So the paging will reduce over time, and this becomes easier. But still, even, I mean, initially you still have to take care about these massive amounts of paging requests, and even for a small operator like E+, this is already 400 pagings per minute. For Vodafone, it's even more. So we are not that fast. So currently, the implementation I have takes around, I think, a second to do the complete attack. This is mostly because once you send the response, you have to resynchronize to the paging channel again to see new messages. And the downside of this as well is that while you are on a dedicated channel and you send the paging response, or you resynchronize, you don't see new pagings anymore. So this is really not feasible with just one phone. We can, at maximum, I think, handle around 60 pagings per minute. But the nice thing, I already mentioned this before, is that these phones are extremely cheap. So I wanted to spare you the technical, the mathematical details about this, but we actually try to determine the number of phones, and for a small network like E+, you need around 10 to 15 of these phones to attack a complete location area. Yeah, so the conclusions I take from this is like attacking single subscribers or even large areas in GSM for mobile terminated services is really feasible in practice. You can even hijack services, and mobile terminated services really need to be authenticated all the time and also done correctly, unlike in the case of O2. And one thing I see with GSM standards is they don't take active attackers into account, so they just don't expect that you have a modified phone and you can do malicious stuff. So this is bad, I think. So I want to thank the following people: Dimitri mostly for the title of this talk, and the other people from the Osmocom community. And with that, I'm open for questions.
We have 2 microphones, so please cue yourself if you have a question. Okay, so we will start with my right. Your question.
On one slide you had you showed the location areas and they were overlapping.
Yeah.
So is it may be that the phone is registered to multiple location areas, or is just one selected?
So it's just once, but it may switch between those location areas. So in practice, at least for Berlin, if you want to attack a whole city district, you may have to attack 2 of these location areas. Even though, given the amount of phones you need for that, I still think this is pretty feasible.
And the second question, I read some pages on the Osmocom website, and there is like you have to modify the Motorola phone for the filter to also receive like.
Well,
is it necessary for this project?
No. For this you don't need to do this modification. This is mostly interesting for sniffing.
Okay, thanks.
Okay, we will continue with my second right.
Did you try to just forward the SMS such that the receiver doesn't notice? Or can you
Sorry again, I didn't get the question.
Did you try to forward the SMS such that the receiver cannot notice, or is it possible to spoof the sender of the SMS?
Yeah, so I mean, of course, like the possibility to hijack the SMS in practice means you can basically do man in the middle on SMS, because you would just grab the SMS messages, and there's again external services which allow you to specify the sender of the message, and you know that from the message you grabbed over the air. So in theory, you can just use one of these services, spoof the sender, and modify the SMS message. Also, you can, depending on how you reply to the protocol, you can still make the message arriving. So if you don't hack all the transmissions, you still get the content of the message, but the message will still be sent to the subscriber.
Okay, your question?
Is the location area the same as the area covered by 1BSC? Because I've read elsewhere that, you know, when the paging request comes in, then the MSC cures the BSC, and whatever BSC had the user last time, it sends the paging request, and then if the user has not been there, then you know
this actually depends on the network configuration. So this is always a trade-off between putting more load on the paging channel and having more signaling in the network. So depending on how your network is configured, one thing that some networks may do, if they don't reach the subscriber within the location area, they start to broadcast paging in bigger areas. So for example, the whole area for the MSC, but this is configuration dependent.
But the location area is the same as the BSC, as the area covered by 1BSC.
I have no idea. I don't know if the BSC is in any way tied to a geographical location area. I wouldn't think it's the case.
Okay.
Also, one VLR is not specifically tied to one location area. In practice, they sometimes handle multiple location areas.
But still, you can confirm that all of the users within a location area receive the same paging request in most of the cases.
Well, in all cases.
Okay.
Yeah.
Okay, next question.
Okay, 2 questions. First, so if you have to be only in the same location area to kill the mobile client,
Okay. And the second, did you think about using two phones? The one will be synchronized with the broadcast channel, and the second will be killing all the clients.
Well,
So you can skip the frequency adjustment part.
So is that because you would need? Well, I'm not sure what the aim of this would be. Would it be because then you have one phone just monitoring and distributing the mobile identities to other phones? Which
Yes.
yeah, you can do that. And in theory, you don't want to do that because then you would need to communicate between the attacking phones again over serial, which isn't fast. So chances are good that you lose the race. But in practice, if you look at how the TIMSI actually isn't completely random. It depends on the time and a lot of other configuration things. And we actually also looked at the TIMSI patterns you can observe over the air. And there's an almost uniformly distribution between sets of values or bytes that are part of the TIMSI, and you can just use that. So this is why our code supports reacting to TIMSI ranges, because then we can just say if the TIMSI, if the fourth byte of the TIMSI, which provides the almost uniformly distribution, is like 1, we just take this phone and this only reacts to this paging. So you can use this to distribute it without any communication between the phones.
And the last one, can you blindly broadcast paging answers? So you don't listen to the paging requests, you are just blindly choosing the TIMSI randomly and you're just broadcasting the answer.
But that wouldn't get you anywhere because chances are good that you send a TIMSI back which the network doesn't know anything about.
Oh, okay, thanks.
Okay, next question on that microphone.
Would this work with modern 3G phones?
So in theory, paging works exactly the same in 3G, so it should also be affected, but 3G network is not the same as GSM network. So for example, if a phone is currently using a 3G cell, you don't see the paging for those. Even though if you're not on a data connection, chances are high that your phone is using GSM because it saves battery.
Thank you.
Yeah, question? Yeah.
The question from the internet?
Yeah.
The question is, how easy would it be for mobile phone GSM operators to practice vulnerability?
Okay, so
Maybe repeat the question.
1, 2, 1, 2. Let me just repeat it. How easy would it be for mobile phone GSM operators to patch this vulnerability?
It's not really easy without changing the protocol because the paging response is completely unauthenticated. The only thing that, well, it depends on what you try to achieve. So if you want to patch the service hijacking, you can mitigate this by authenticating 100% of the time. If you want to patch the denial of service, you would need the paging response to be authenticated. So one thing could be patchable in practice, the other thing is not patchable without changing the protocol, which is not realistic for GSM.
A question?
How does the client control which paging requests he will receive from 3G or GSM? So
I didn't get the question, sorry.
I'm very a novice to mobile communications, but if you said that if if the phone is using 3G, you only receive 3G paging requests.
It's because it's just camping on a different cell then. So it's just camping on a 3G cell, so it doesn't see GSM. So actually I also looked at that because I assumed that it may be that the network doesn't differentiate here and it just broadcasts paging messages in 3G and GSM cells at the same time, but it's just broadcasting this on 3G cells. So if you're on a 3G cell, you don't see this.
And can you spoof the request to receive GSM paging requests?
That's a good question. I don't think you can do that without having a stronger signal than the actual cell. And the chances are good that you have collisions and this doesn't work in practice. But I don't know, I haven't tried.
Okay, thank you.
Any more questions? Well, then let's thank the speaker
Thank you.
again.